Hi everybody. I just want to very quickly derive the equation that we are going to use in our lab this week. It's an equation called the range equation. And what it describes is for an object fired at a velocity, let's call it v sub 0 at an angle theta, it tells us as long as it starts and ends at exactly the same height, what is the range? We'll call it r. We've usually called this x final. But now when we start and end at the same height in this particular situation, we're going to call it the range r. So I really want to stress this equation applies only for 2D projectile motion where you are starting, let's say, on the ground and ending on the ground, or starting at some height and ending at exactly the same height. It won't work for situations where you're shot off a cliff or where you're like potentially fired up at an angle or down at an angle and you land at a different height. It won't work for either of these. Okay, so let's see if we can go ahead and derive these. So first of all, remember with projectile motion, the horizontal, the x motion, is constant speed. And so it's governed by the equation, the horizontal range r is just equal to the v in the x direction times the total time. Whereas the vertical motion is equal to, is free fall motion, and that's going to fall under the big 5 with the acceleration equal to negative g. So the first thing we need to do here, if you remember, is break that initial velocity into two components. And let's break it into a v in the x direction initially. I'll call it vx sub 0, but in reality we don't need the sub 0 because the velocity is constant in the x direction. And let's break it into the v initial in the y direction. And there we actually do need the initial because, as you know, as it rises, the velocity is going to decrease in the y direction. It's going to be momentarily 0 in the vertical direction at the top, and then it's going to come back down and be the exact opposite as it was when it was launched. Okay, so here we are. Let's write those first. Vx sub 0, if you remember, is just going to be v naught times cosine of theta. And vy sub 0 is going to be v naught sine of theta. And you could take a minute and remind yourself of those two things if you need to about how the vectors and the initial conditions work. Okay, and this is forward and this is up. And so let's do our first equation. Our first equation then is that Vx sub 0 times t equals our range because the horizontal motion is just constant speed. So let's go ahead and plug in for Vx sub 0, v naught cosine theta is equal to the range. And remember, our goal is times t is equal to the range. Now, the idea is to try to have, we could stop there, but we want to actually see if we can make this a time-independent equation. We want to see, what does the range really depend on? What initial variables? Does it depend on the initial speed? Does it depend on the angle? We know it probably depends on both of those things. Can we get an expression that doesn't include time? So let's look at our second bit of information. If I start here and I end here, let's look at our y values. Our initial y position, I'm actually going to call it y sub 0. Be consistent. Y sub 0 equals 0. Our y final is 0. I start and end at the height 0. So let's see if we can use one of the equations. And I'm going to start with the delta y equals v initial in the y direction times t plus 1/2 at squared. Now let's see if we can first fill in the delta y. Well, they're both 0 and the delta is 0, so this side is 0. And don't let that scare you, it's totally okay. For the v naught y, I can put in v naught sine theta. This is looking good. And then my a, remember, is negative g in the y direction, so that becomes minus 1/2 gt squared. Okay, so I have this equation, and I have this equation, and I'm going to go to a new page, and I'm going to write them both down again. Okay, so my two equations are V naught cosine theta, that's Vx, times time equals the range, and then delta y equals V naught y, which is V naught sine theta, times t minus 1/2 gt squared. Now, in looking at this, I can't do much here, but I'm going to come over here and rearrange this so I get V naught sine theta times t equals 1/2 gt squared. And as long as t is not equal to 0, I can cross out one of the t's, and I get V naught sine theta equals 1/2 gt. So I'm going to solve that for t. T equals 2 V naught sine theta over g. And now I'm going to come and plug that in up here. And that gives me V naught cosine theta times time, which is 2 V naught. Oop, that doesn't even look like a V. I don't even know what that is. Erase that out. 2 V naught sine theta over g, that was just t, equals the range. And I'm going to simplify that a tiny bit more. 2 V naught squared sine theta cos theta over g equals the range. And I could stop there, except 2 sine theta cosine theta is a trig identity. It's equal to the sine of 2 theta. So I'm going to simplify this one more time. The range is equal to V naught squared sine of 2 theta over g. Notice that does not depend on time. And so what it tells me is where I'm going to land if I know my initial velocity and I know my initial angle. And so in the lab, we're going to actually explore the relationship between range and theta for a constant launch velocity. And then we're going to see if we can use this to calculate the launch velocity. That's what we're going to do in the lab. Now here's another really cool fun fact. What is sine of, let's say theta was 30 degrees. Okay, sine of 2 theta is sine of 60 degrees, right? Now, let's say theta was 60 degrees. Sine of 2 times 60 is sine of 120. So it turns out, though, that sine of 60 and sine of 120 are the same sine. And so if you start to plug in numbers for theta, you actually realize that the r is the same for complementary angles. Complementary angles. So if the angles are complementary, so 30 and 60, 20 and 70, and you plug them in here, you'll find that they have the same range. And we will talk about that a little bit in class the day we do the lab. All right, that's it. I hope this was helpful, and I will see you soon.